We have just finished up with derivatives by definition and using the rules. Now what we're going to do is get into a little bit more exactly what that derivative means. Even though we've already talked about its initial meaning, how are we going to use it? How are we going to apply it? So the first part of this is just remember what a derivative is. What did we talk about in terms of identifying that? So let's go over this a little kind of quickly, but tangent line is the line that best approximates the slope of the graph at a single point. But to do that, we've always learned that you needed 2 points to determine what the slope of the line was. So we started with a secant line, a line that intersects the graph at 2 points. And what we determined was, with this point being x, and then the function being f of x there, then we have that point. And then this point, we said the distance would be h, so this would be x plus h, and then f of x plus h. And remember, I've already done this in the previous video, so go back and watch that if this isn't making sense. But to find the slope of that line then, we know that the slope of the secant line is equal to the change of y, which is f of x plus h minus f of x, divided by the change of x, which is x plus h minus x, and the x's would cancel, and then you're just left with h. So that's the slope of the secant line. And then what we had decided was, if we take the secant line and we keep changing the h value to be smaller and smaller and keep making this difference smaller and smaller, then what happens? We're getting closer and closer to the actual tangent line. So as h approaches 0, the secant line approaches the tangent line. So therefore the slope of the tangent line then would be the limit as h gets closer and closer to 0 of the slope of the secant line, which would really be equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. And there's that difference quotient that we had talked about previously as well. So this right here represents the derivative of that function, whatever it might be. So now the question is, how do we use that? Alright, so let's take a look. Find the slope of the tangent line of f of x equals 2x squared plus 3x plus 1 at the point 1 comma 6. So what do we need to do? Well, the derivative helps us identify what the slope is at any given point. So what do we want to do at the point 1 comma 6? Well, let's go ahead and find the slope, or the derivative first, of the original function. So the derivative of f of x would be 4x plus 3 and then plus 0. So the derivative of a quadratic is linear. But that doesn't necessarily give us that slope. We don't at least seem like. So then what do? Well, because we're looking at a very specific point, we're looking at when x equals 1, this represents what I'll continue and talk about as saying this is the slope formula. Okay, this derivative gives us that slope for any value of x. So I'll say for all x values. If I want to know specifically what the slope is at a certain x value, I'll just plug the value in, which in this case is 1, and we take 4 times 1 plus 3, and so the derivative at x equals 1 has a slope of 7. So this is a slope of 7 at the point 1 comma 6. And we could do this for any point. I could say, all right, what is the slope at x equals negative 1? Now it's 4 times negative 1 plus 3. And that would be negative 1 also. So that means that the slope is negative 1 at, I don't know what the point is, but I know it's at x equals negative 1. So we could find all sorts of points and slopes. I'll go back. We can find all different values of the slope at different points on the graph, okay, of this quadratic. So with a quadratic, we will get some negative slopes, and then we'll get some positive slopes, and we'll even get a slope of 0 at the vertex. So that's what we're doing, is being able to find the slope, which is the rate of change of any point of any graph using the derivative. So let's add to our last question. Find the slope of the tangent line of at the point 2, 6. So far that question is the same. So if you want to pause it and try it yourself, go ahead. Different function, it's a cubic. So when we find the derivative, we'll get a quadratic. But we're still finding at the point 2, 6. So let's go ahead and find the derivative of the function, which would be 3x squared minus 1. And then just like before, if I'm trying to find the slope at a given value of x, which is x equals 2, I'm just going to plug 2 into that formula for the slope of any value of x. And what do we find out? 3 times 4 is 12. 12 minus 1 is 11. So we know that the slope is 11 at the point 2, 6 of the function x cubed minus x. Now we're going to take a step further. Write the equation of the tangent line. Well, this just gets back to your linear algebra, or your algebra with linear equations. Is if I have a slope and I know it goes through the point 2, 6, how do you write an equation of a line given a slope and a point? One of the ways is you can use the point slope form and plug in your y value, your slope, and then your x value of the point, and then solve for y. So distribute and then add 6. Alright, and so here's the equation of the line, of the tangent line, through the point 2, 6 with that slope of 11 at that given point. So just to kind of add on in terms of what we are already looking at. And then the last example, I'm just going to give you a function and ask you to write the equation of the tangent line at x equals -1. So obviously, just like we did last couple, we need to start by finding the derivative. So that'll be 4 times 2 is 8. Subtract 1, so that's 8x cubed. 3 times 3 is 9. Subtract 1 is x squared. 4 times 2 is 8. Subtract 1 is 8x to the first, and then 1 times 2 is 2. Subtract 1 be x to the 0, which is just 1. So 1 times 2 is 2, and then you got your constant. So there's the derivative. We don't have a point, but we have x equals -1. So we can go ahead and plug in at x equals -1. We can evaluate this. That'll give us -8 minus 9 minus 8 plus 2. So f prime of -1 would be equal to -16, looks like -23. So what do we know? We know that the slope of the tangent line is -23 at x equals -1. We don't have the point though. So if I want to write the equation of the tangent line, I need to know what this y value is. Well, how do you find y when you know what x is? Well, you plug it in. Now, I'm plugging -1 into the function. When I plug -1 into the function, how is that different than plugging it into the derivative? So think about that. By plugging -1 into the function, what does my output represent? But when I plug -1 into the derivative, what does it represent? So when I plug -1 into the function, that gives me the output. So I now know that the y value is 8. When I plug -1 into the derivative, -23 represents the slope. So we know the point now is -1, 8. So now we can go ahead and write the equation of the line. Y minus 8 is equal to your slope of -23 times the quantity x minus -1. Distribute. And then add the 8. So we get y equals -23x. Add the 8 and we get minus 15. So the equation of the tangent line of the function at the value x equals -1 is y equals -23x minus 15. All that stuff, in terms of the first part, is finding the slope. So we first found the slope using the derivative at x equals -1. We then plugged -1 into the function, which allowed us to find the y value, so that we had the slope and the the slope and a point, and then we were able to use that to write the equation of the tangent line. So that is it for tangent lines to a graph. Once again, focusing on, can you write the equation of the tangent line? Can you find the slope of the tangent line at a given x value? And once again, understanding that the derivative represents that slope formula for any value of x on that particular function.